illustrate how we can introduce events in VCell and also show some interesting model behaviors like switch bistability and hysteresis. I will share my screen now. And okay, so here is the model that I'm using. Let me make this bigger. And okay, so this is an extremely simple model. We have an enzyme E that can be in two different states, unphosphorylated and phosphorylated. And there's two reactions. The phosphorylation reaction obeys simple Michaelis-Menten kinetics. The dephosphorylation reaction also obeys Michaelis-Menten kinetics. This is a very common occurrence in a cellular system where we have a kinase and a phosphatase that catalyze the phosphorylation and dephosphorylation of proteins. And typically, the phosphorylated and unphosphorylated state of the proteins have different behaviors and can be responsible for different cellular actions. So, in addition to these two reactions, this model explicitly introduces the kinase that catalyzes the phosphorylation reaction, which can be regulated. Often kinases are regulated in various different systems, and assumes that the phosphatase that catalyzes the dephosphorylation is constant throughout the simulations in this model. So we see that in the Michaelis-Menten kinetics of the phosphorylation reactions, the Vmax depends on the amount of the kinase, which is R. And the kinase is modeled to be synthesized just like any protein by some constant reaction rate, and also degraded according to simple mass action kinetics. But there's a twist here. The twist is that the unphosphorylated form of E actually stimulates the degradation of the kinase. And let's see how the system behaves first. So let's take a simple application. Let's set the enzyme at the beginning, all in the dephosphorylated state, and let's pick a random amount for the kinase. Let's say it's 1. And let's run a simulation to maybe 100 seconds to reach equilibrium and see what happens. Need to move this Zoom panel a little bit out of the way to hit the button. And as you expect, the system will settle at some value, steady state value of the phosphorylated form and the unphosphorylated form. So for the value of R that I've arbitrarily chosen as 1, it looks like the system settles with E in mostly unphosphorylated state, and then and very little of the phosphorylated form. So obviously we can edit this and see what happens at a higher level of kinase. So let's say we do the value of S, not 1, but let's say 4. Okay, and we run this. And now you can see that compared to the previous one, the steady state reached is kind of the opposite, where most of the enzyme is in the phosphorylated state and very little in the unphosphorylated state. So you might want to ask yourself, well, let's explore this a little bit more, because this is a very powerful difference by just changing a value from 1 to 4. So let's explore this by doing a parameter scan with different values of R to see why there's such a huge flip in the steady state. So what we can do, obviously, as you all know, is like, okay, let's scan for different values. So let's start with a value of 0.2 and go all the way to maybe 3 and give me 15 values. So this will essentially do it for 0.2, 0.4, 0.6, etc., etc. And say, okay, and rerun this. And here, if you probably know by now that there is this little button that allows you to multiple select between the parameter values and plot the values of your species of interest under different parameter values. So I'm going to open up that window, this view, and say, show me the phosphorylated amount of the enzyme for all different values. So what you can see here is that all the values up to the green one, which is set 7, right? So when the value is 1.6, are very low values, and then suddenly you increase a little bit more the value of R, you reach steady state at very high levels of phosphorylation. So this is a classical example of a switch-like behavior, which is the result of sort of bistability, where you have a stable steady state in 2 very different regimes. So how are we going to connect this with events? Well, let's make things a little bit more interesting. Let's assume that we want to actually control over time the value of R, and controlling it by changing the synthesis rate, right? So what we can do, go back, under protocols, there are several different tabs that you can, in an application in Virtual Cell, you can control various elements of the systems programmatically. The first tab that opens when you open it up fresh is the electrical panel, which is if you're modeling electrophysiology, it can deal with electrodes, voltage clamp, current clamp. The next one is events. So events is a formal way of describing a discontinuity in the system in one of several different ways. So let's introduce events. So a new event. So the first thing when you're trying to show a event, trying to define an event, it asks you, what is the trigger? When does this event trigger? So you have several different options at a single time. When a variable exceeds some upper limited or falls below a lower limit, any list of times like 0 at 0, at 1, at 1.5, or you can do a linear time range and or log time range, or put an arbitrary condition, say the concentration of variable X becomes greater than the concentration of variable Y, and so on. So this is very powerful. You can define many different trigger conditions. So in our case, let's just say we're going to use a trigger to slowly increase the value of S. So let's say we'll start at 50 up to 1,000 seconds and do it for 20 times. So this tells you that this trigger will fire 20 times every 50 seconds, starting at 50 seconds of simulation. Okay, that's step one, is the trigger. Step two is, okay, what do you want to do when the trigger fires? So these are the actions, and you can use one or more actions that are triggered by the same trigger. So there's also a little delay option, so you can say certain things happen a few seconds after a particular trigger and so on. So let's add an action where we want to modify the value of S. And just in very simple coding or scripting, you can just say S plus 0.2. So essentially, this will increment the value of S from whatever it was before the trigger at trigger time by adding 0.2. And let's go back to our specification and say, let's start with S at the value of 0. And our simulation, obviously now we want to run it for, let's say, 1,100 seconds. And run this. Oh, let's cancel the scan because the scan now is irrelevant. And run this and change the default x-axis. You show us 1,200 seconds. So what you can see is actually not very surprising, because we already did this parameter scan that shows at what value the phosphorylated concentration of E will settle. So obviously for the first 50 seconds, it stays at 0 because S is 0, so there's really nothing going on. And then after the first trigger, it will settle at some low value, a little bit higher, a little bit higher, a little bit higher. And when it reaches this value here, suddenly jumps at that. And we can take a look at what value of S that happens. So again, when we jumped from S is 1.6 to 1.8, it went over to the other side. And then any additional incremented S actually produces very little change because it's almost 100% phosphorylated. And we can plot the unphosphorylated concentration of E and see the opposite effect. Now, let's go back to events to say, well, maybe we can add another event and do again a linear time, but start at 1,050 and go to 2,000 and give me another 20 values. So now this event also triggers 20 times, but starting after the first 1,000 seconds. And we can add an action where we want to, this time, decrement the value of S. So let's say S minus 0.2. And let's go back to our simulation and let it run now for 2100 seconds. And sort of as expected, we see that the value of the phosphorylated states for the first 1,000 seconds happens as before, and then S is being decremented, and then with the same amount of sort of suddenness, it will come back to the lower steady state.
Jan,
Yes.
would there be any value in doing a plot where you change the x-axis to S?
Yes, that will be my immediate next step.
Oh, okay.
Yes, I will do a phase diagram right after that. So what you may notice here is that this doesn't look symmetrical. So for the first 1,000 seconds, we increased the value of S, and there was a certain value here at about 1.6 to 1.8 change where we jumped up. But then it looks like it kind of took longer until we came back down. So let's actually verify that by plotting the value of S also. And yes, here was the jump when we moved from 1.6 to 1.8, but it fell down only when we moved down from 0.8 to 0.6. So the steady state of the system, whether it is in the higher regime steady state or lower regime steady state, the switch happens at different values of the regulatory parameter S. If we are on the upswing or if we are on the downswing. So it will take a bigger change in S when we increase it to move into the upper steady state, and the bigger decrease required to come back down when you come back down. And this is why this behavior has been nicknamed a toggle switch. So, if you think about the switch, your light switch, you have to apply some pressure up to a point where it suddenly then jumps in the other part, and then you have to apply some more pressure going down till it jumps to the other part. So now we can plot things in a more interesting way, as Les had alluded to earlier. The x-axis doesn't have to be time. Most of what we've seen so far are regular time plots, but we can say, well, let's see how does ephos vary as a function of S. So this is as a function of time, but we can say as a function of S. And we get this little phase diagram where it shows you what are the values at which the steady state happens in relationship to S. And you see here, the lower part is we increment and then we finally jump up at 1.8, and then when we come back down, it's about 0.8 where it jumped back down. And this behavior is called hysteresis. And the same way we can plot R as a function of S or these two as a function of S. And you see the symmetrical hysteresis between the phosphorylated and unphosphorylated state. So I think I'll stop here with events and take any questions. Pedro had mentioned about, the cloud use, the command line use of virtual cell. I don't think this is quite as ready as Capacity with Pasico at this point for a general purpose presentation. So if anybody is actually interested in running a containerized version of virtual cell in command line mode on their own cluster and programmatically script or code functions of that, I would suggest you get in touch with Jim, Logan, or myself, and we can discuss that. I would not advertise this publicly at this point, at this stage.